If you work with anything that spins, I'm talking from a tiny motor all the way up to a giant industrial roller, you know that sound, right? That little hum that turns into a shake, that rattle that can spell absolute disaster. Well, that vibration, that's the enemy. And today, we're going to look at the tools we've built to defeat it, balancing machines. Specifically, we're going to answer the biggest, most fundamental question you'll face. Should I be using a horizontal or a vertical machine?
You've probably been there. You get a brand new part, looks totally perfect to the naked eye, and you get it installed. But the second it spins up, the whole assembly just starts to shake and rattle. So what is going on? Is it a bad design, worn out bearings? Well, the real cause is usually something much, much smaller and way more fundamental.
That's it. That's the whole thing. Imbalance. Just a tiny, almost invisible bit of extra mass in exactly the wrong spot. This is the hidden enemy we're fighting, and the tools we use to conquer it are these high-precision balancing machines. They're built to find that imbalance and tell us exactly how to fix it.
Okay, so you know you've got to balance a part. But which machine do you grab? This is really where it all begins. The choice between a horizontal and a vertical machine, it's not some minor detail. It is the absolute key to getting an accurate, efficient, and reliable result. If you can understand this one distinction, you've pretty much solved the whole puzzle. The entire difference between these two families of machines really just boils down to one simple concept: spatial orientation. Or to put it even more simply, which way does the part spin? Is its axis of rotation parallel to the ground, kind of like a log rolling downhill? Or is it perpendicular to the ground, like a spinning plate on a table? This one single factor dictates everything else: how you load the part, the type of imbalance you can find, and even which parts the machine can handle in the first place.
Let's make this super clear. Over here on the left, we've got a horizontal axis running parallel to the ground. A perfect example is a car's drive shaft. It's supported on both ends, and it spins along that horizontal line. Now, on the right, you've got a vertical axis, perpendicular to the ground. Think of a spinning top. It's supported from the bottom, and it spins flat. This orientation, this is basically the DNA of a balancing machine.
All right, let's meet our first contender, the horizontal balancing machine. And just like the name says, this machine is the specialist for parts that are really defined by their length, things that have a clear shaft or an axle. So, because a horizontal machine supports a part at two different points, it's got this unique superpower. It can detect what we call couple unbalance. Now, this isn't just a simple shake. It's this destructive wobble, where an imbalance on one end of the part is literally fighting an imbalance on the other. This two-point support also makes them incredibly versatile for different lengths. And what's really crucial is that they often balance the part in the exact same orientation it'll be in when it's actually working, which is a huge advantage for accuracy. But, they're not perfect for everything. Trying to maneuver a long, heavy part onto its supports can be a slow, really careful process. You're probably going to need a crane. And what about parts that are more like a disc, ones that don't have their own shaft? Well, you can't just set them on the machine. You have to first mount them on this special tool called a mandrel, which adds an extra step and, honestly, another potential source of error. And here we have the classic example. A motor rotor is the absolute perfect candidate for a horizontal machine. It's defined by its long shaft, right? And it has to be balanced at two different points to stop that destructive wobble when it's spinning at thousands of RPM inside a motor. And you can probably see the pattern here. You've got industrial rollers, big fan drums, vehicle drive shafts, pump rotors. What do all these things have in common? They're longer than they are wide. Their mass is spread out along a central axis. That is the signature of a horizontal workpiece. Now let's flip to the other side of the coin, the vertical balancing machine. If the horizontal machine is the master of long shafts, this one is the undisputed champion of discs, plates, and flywheels. The key word for this machine is speed. Loading is as simple as just placing the part down onto the machine's spindle, kind of like putting a record on a turntable. This makes them absolutely perfect for automated, high-volume production lines where every single second counts. They also usually take up less floor space, and they really shine when handling parts that just have a central hole but no shaft. The machine's fixture centers that part with incredible precision every single time. But its limitation is just as clear as its strength. You simply cannot balance a long workpiece on a vertical machine. I mean, just imagine trying to balance a broomstick on your fingertip. It's just inherently unstable. That high center of gravity would cause the part to wobble like crazy, making an accurate measurement totally impossible. It's just not what they're built for.
And here it is, the perfect example of a vertical workpiece, a brake disc. It's flat, it's wide, and it's all about that rotational symmetry around its center. You need to balance it in one plane, and you probably need to do thousands of them a day. This is a job that is just tailor-made for a vertical machine.
And again, you see the pattern, right? Impellers that move fluid, cooling fans, pulleys for belts, heavy flywheels that store energy. They are all wider than they are tall. They are disc-like. Their mass is all concentrated in a relatively flat plane. That's the world of the vertical balancer.
So we've got our two main types of machines, and each one has some really clear strengths and weaknesses. So how do you actually decide which one to use? Well, it might seem complicated, but the choice is actually incredibly simple, if you know what to look for. Now here's a really important point. Both of these machines operate on the exact same principle of physics. The science of centrifugal force, all that math, it doesn't change. So the decision isn't about which machine is somehow scientifically better. No, it's all about which machine is practically better for your specific part and your specific production needs.
Think of this slide as your cheat sheet, breaking it all down. Just look at the key differences. Rotation axis, horizontal versus vertical. Workpiece shape, shaft-like versus disc-like. And this is all captured perfectly in what's called the LD ratio. Length is greater than diameter for horizontal, diameter is greater than length for vertical. And this all dictates the correction. Horizontal machines are fantastic at two-plane or dynamic balancing, correcting that wobble we talked about. Vertical machines, on the other hand, they usually focus on single-plane or static balancing, which is perfect for flat discs. And here it is, the ultimate takeaway, boiled down into 3 easy steps. Step 1, look at the shape. Is your part basically a stick, with its mass spread out along its length? Go horizontal. Step 2, look at the shape again. Is it more like a disc or a plate? Choose vertical. And finally, step 3, look at your volume. Do you need to hook this up to automation for high-volume production? Well, the speed of a vertical machine is almost always going to be your answer.
You know, it really doesn't get any simpler than this. This quote just captures the entire essence of the decision. Forget all the complex terminology for a second and just look at the physical shape of your part. Is it a stick or is it a plate? Answering that one simple question will get you to the right machine 99% of the time. And that leaves us with one final thought. We spend so much time comparing all the features and specs of the machines themselves, but that's really starting in the wrong place. The right question was never which machine is better. It was always, what is the nature of my workpiece? If you can answer that, the right machine, well, it'll choose itself.